Welcome. Class 2. Today we're going to talk about timers, inputs, the blackboard for the game, and we're going to introduce a system that allows us to do movement, and that will lead us up to your class exercise. Before we start, curiosity is your friend in this class. You paid a lot of money to be here. You're all paying good money to be here. The money doesn't buy you a grade. You can get the grade. It buys you time and structure to dig into a hard topic with people who care. That's me. So the question for you in this class is, will you do that? Will you take the time to go beyond just getting the grade to understand this topic? I am giving this course in the world of ever evolving large language models. It doesn't matter how complex I make the assignment, you can delegate the work of completing the assignment to the large language model, and then you can do it. I'm not even going to pretend that this is otherwise. So the honest assessment of what assignments are right now is they are a map to the beginning of your journey, not the destination. An assignment says, here's an idea worth exploring. In this particular class, we're going to introduce the concept of movement. Then after you satisfy the requirement that you've done an assignment that demonstrates that you understand this, then you can build something. You can start thinking about it, looking at the code, and playing with it. Every class GitHub repo is independent, so you can do whatever you want with every class, because the next class you get code that works, so you can completely break the class and then you can go to it. So don't stop with, oh, I've passed the test. Let your curiosity drive and take you in to the other side where you actually are learning about games. You're thinking about how this new way of representing data and processing data works. You can paste the prompt into an LLM, submit the output, and get a passing grade. I can't stop you from doing that. I'm not even going to stop you. I'm not even going to try. The transcript doesn't demonstrate what you know. If you are in an interview with a game company and they're asking you about patterns in game engines, and you start to talk about this course, and all you have to say in the course is, I got an A, that doesn't get you the job. But if you can talk about the experiments that you do every class, the things that you do, the things that you share with your teammates, and how that all led to a deep passion for understanding how games can work, how the ECS pattern works, that is what's going to get you through the door into that interview. After you finish the exercise runs, ask one more question to yourself. What if I change this constant? Why a bug when I remove that check? Can I break it, unfix it? The loop, change, observe. That's what you are actually here to do. You're here to have fun with that. And that's what the Piazza room is for. Share your knowledge. If you do an experiment, share it with other people. Say, hey, I did this thing here. You can share code here. There's nothing that stops you from giving code away. There's nothing that stops you from sharing your learnings. So the LLM is a partner for you. You have a guess. Make up a hypothesis, then ask the LLM to challenge it. Here's my mental model. Where am I wrong? So, for example, you could say, I believe that my rectangle will bounce off all walls correctly. Can you show me in my code that that is correct or incorrect? What edge case did I miss? Am I going to bounce off the top? That's apprenticeship. That's the world that we live in, where you're thinking about the systems of the game engine, not just copy-pasting stuff to get your grade. So you're spending the money to be here. I can't force you to learn. No professor can. What I can do is build a path, and that's what I've tried to do, where the interesting questions are what you can then reach. Walk through the doors, get the assignment, and then be curious and play with the code and see how you can make fantastic things happen and understand the systems that I'm introducing step by step. That's how you get your money's worth from this course. Okay, So, here we are at the beginning of this class. At the end of this lecture, you will be able to explain why 60 frames per second is the standard for games and how frame budgets work. You'll be able to describe the sleep and busy wait technique for precise frame timing. The STL thing provides one for us, but we're going to implement our own just so you can see how it's working. We're going to implement keyboard input handling using STL events and ECS components. We're going to define a blackboard pattern and explain why we use it. We will talk, last lecture we talked about a big spreadsheet where we have the entities are rows and the cells are either empty or they have a link to a component. The blackboard is going to be a similar thing. It's a shared piece of data that every system can go and look at and say, oh, there's this shared piece of data. So, you know, the time that the game has been running is not something you want to attach to every entity in the system. You want to have a global variable for that. Yep, I said global variable. We need to have global variables in this. I know that's what we told you in CS 101, that you're not supposed to have global variables. We are going to have global variables. And then you'll be able to understand and talk about the data flow from a keyboard input to on-screen movement when we get to movement at the end of that. Okay, so lots of stuff to work. Let's get going. Okay, section 1, the timer, 60 frames per second. This is a very, very key component of modern games, and we'll explain to you why. The reason that we are going for 60 frames per second is to provide a smoothness of motion. So human eyes don't see animations. We retain images, and our visual system puts that together into perceived movement. So if I show you a photograph and then a second later I show you a photograph, you see two distinct images, and your brain doesn't collect those things together into motion. If I show you 25 photographs in 1 second, then our visual system starts to see this as smooth motion. So we could go with 30 frames per second. That would give us quite a bit of time. Each frame has 33 milliseconds, and what's going to happen there is that your response to what you see on the screen is going to feel sluggish. If you ever work on a 30 hertz monitor and you're typing, you'll notice that things are kind of slow, and you're going to the feel of interacting with something live just isn't quite there. And sometimes you're going to see panning, it doesn't look quite perfect. So 60 frames per second gives us a really, really responsive input. It feels instant, like 16 milliseconds isn't that much time. That's how much time we have per frame, and the objects are moving in smaller increments. And so the other thing is that many of our monitors, in North America at least, had a 60 hertz refresh rate. In Europe, they had a 50 hertz refresh rate. That's changed now that everything is digital. So 60 frames per second is what we're trying to get, the smoother. So let's have a look at that. So here we have we have some objects that are moving across the screen at exactly the same speed. They're 250 pixels per second. But what we are doing is we are displaying them at a different frame rate. So in the top one, we display the position of the square every 200 milliseconds. And you'll notice that the top line, if you just look at the top line, it doesn't really look like something that's moving. It's it's just appearing and disappearing. Now we move down to 10 frames per second, and now you're starting to see something that's you can feel that it's moving, but there's still enough jaggedness in the movement that your eye sees kind of a combination between something that's moving and snapshots of something that's moving. At 15 frames per second, you're starting to see a little bit smoother. 24 frames per second, it's starting to see, but you notice that we haven't crossed that 25 frame per second. Now, if you look at the difference between the 30 frame per second and the 60 frame per second, you just put your hand over the screen and you can just look at those two. You see what I mean by the 30 frame per second. It looks like a smooth animation, but there's just something not quite as beautiful about it as a 60 frame per second. So that's basically what we're seeing here. And that's what I said. We saw there was a seamless movement from 30 to 60 frames per second, and that's kind of the gold standard. If you're running a stereo game, then you're running at 120 frames per second because you render one image for the left eye, one image for the right eye, and so you only have like 8 milliseconds to do all of your computation. So that's quite good. So let's agree that we're going to do 60 frames per second, okay? And so at 60 frames per second, we have 16.67 milliseconds. So typically you have a budget. You have only so much computing that you can do. The first thing that we do, as we saw from the game loop, is we process the input. Then we update all of the database for all of our game objects based on the user input, whatever objects are moving, whatever physics is going, whatever AI is going. And then we take all of our geometry and the system, the render system, displays that to the screen, and then we have some time left over, so we're going to wait for 2.67 milliseconds, right? So we've got a total of 16.67 milliseconds. So why do we do this like this? How do we implement it? The way that we implement it is we get the current time. We basically say, okay, what is the time right now? Then I handle the events. I run my update, which executes all of our systems, the ones that we're going to build throughout this course, and then we render. Now, if we have designed our game right, if we are actually able to run at 60 frames per second, we then look at our target frame time, and then we determine a delta, the amount of time that we have left. So, and then what we're going to do is we're going to wait, right? So, here's the first implementation. All of our operating systems have sleep functions, right? So in C++, we can ask for a thread to sleep for that amount of time. So the problem with this is that this is an operating system call, and it's kind of accurate, but it's not precise. The OS doesn't guarantee exact wake-up times. When you call sleep, the OS takes your thread from the CPU scheduler and then marks it as sleeping. So your code isn't even running for that amount of time. And then around the end of the sleep time, it says, oh, okay, I've gone from this job to this job. I'm going to pick up this thread. I'm going to put it back into the queue. And then when its turn comes around, it will wake up. And so you can you can be 0.2 milliseconds late, you can be 0.8 milliseconds late, you can be up to 1 millisecond late. So if you start to just rely on that sleep element, these errors will compound, and you're going to drift from, you're not going to get 60 frames per second, and things will start to look odd. What we do is we use a combination of sleep, which is an inexpensive way to wait because the CPU scheduler just puts us to sleep. And then what we're going to do is we're going to come back and we're going to have enough time so that we can precisely end at 16.67 milliseconds, and we're going to busy wait. And so this is what we're going to do right here. See, here, in this particular thing here, we have this here, this little circle here, is going to wait. So that's our sleep. We are going to uh, call the system. Now notice that we have here, we have a sleep threshold. Now this sleep threshold is something that we determine experimentally. Uh, you want to make sure that this here is going to end before the 16.67 milliseconds, so that we can then do this one here. You notice that what we are going to do is we're going to busy wait. And so what is busy wait? We basically say, while I haven't got to the end time frame. So remember my target time frame here, this target time frame here is calculated as the beginning of the frame plus 16.7 milliseconds. And so then I get this. So this is my frame time, the current time. And so this exits precisely at the right time. So what I have here is a very, very high accurate guarantee that I'm going to get 16.67 milliseconds per frame, every frame. So this is what every frame looks like. You have some game logic here. That includes your input, it includes your processing of all your systems, and it includes your rendering. And then we're going to do this here. And again, in the next frame, we're going to have a sleep. That gets us to kind of, you want to target around 16 milliseconds. So the goal is that by the end of your sleep, you've got enough time to go from here to here. Again, from here to here. We don't trust the operating system to wait for us. So then we do our busy wait here. And then the next frame we do it here, right? So again, let's go back and we look at the code here. Here, this one here, is our call to the operating system CPU. And this is where we go, okay, we're waiting for it. We're going to wait for this. And we're going to say, absolutely guaranteed, we're going to end at the end of that frame. So why do we wait at the end of the frame, right? We could put this thing up here. The reason that we do it here is that this guy here and this guy here, so these two systems here, in general, are not guaranteed to run at exactly the same time. You could have a lot of characters on screen that are colliding with each other, so that's going to take longer depending on how many characters you have. The more characters you have on your screen, the longer it takes to render them. So what we do here is we want to guarantee that the time from here to here is always the same time. And right here, we have a variable set of events that are happening. If you do the optional network module, you'll see that processing the input that the network gets processed there. So what we want to do is we want to have consistent frame boundaries so that we have consistent time. And then our delta calculation is a lot simpler because we calculate the beginning of the frame right here. Then when we get here, we know how much time we have to spend to get from there to there, right? And so that's what we can do exactly this, where we do, this here could be 6 milliseconds, in which case here we would sleep 9 milliseconds. If for some reason we spend 10 milliseconds here, then we're getting tight, and then we would spend 5 milliseconds here. So again, we want to guarantee that the time from here to here is exactly the same time as the time from here to here. Back. So what I just did previously, if you didn't notice, I introduced a timer class. Right here, you see this object, timer, and this object, timer. We're going to encapsulate this functionality in a timer class, and then we will instantiate an object called timer, and then at every frame, we're basically going to have all of the work of the game engine here surrounded by a call to timer start and timer end. Okay, so let's dig into this and see how this is implemented. But first, there's a couple other things that we're going to have the timer class do. We're going to introduce the idea of frame history. And what we're going to do is we're going to store the information for the last 60 frames so that we can calculate two things. The one is this idea of a sleep error. Whenever we call the operating system sleep, it's not precise, as we've discussed before. And what we'd like to do is learn just a little bit so that we can maximize the use of the sleep and minimize the busy wait. Depending on your operating system, et cetera, you're going to be able to optimize this a little bit. It'll save you a little bit of energy. The other thing is that we would like to be able to report our FPS as an average of the last 60 frames. If we were to calculate the FPS based on the time of the last frame, we might have a slight difference. So we might see 61.7, 58.5, 60, etc., etc. So, but what we really want to do is we want to just store the history of the last 60 frames, and then we're going to take the average. And so for both of these things, this here, the sleep error, we really only need the previous frame, but this one here is for stable FPS. In industrial settings, this FPS is one of the marks of whether your game is in good state or not. So how do we do this? Well, we store this history in this circular buffer here. And the way that we implement this circular buffer is with a fixed size array, and then we just have an index that goes over that. So let's have a look at this and see. First of all, let's look at the private members. This right here is the target frames per second, target FPS. This is what the constructor will receive, and it will then calculate this, which is the target frame time. And that is simply 1 over FPS. So it's so 1 over 60 is 16.67. Then every time we call frame start, we set this variable here to be the current time. And then we're going to use this as a delta time, which is the amount of time that our frame actually ran. And then here is our storage for the sleep error. We told you we're going to do two more things. One is we're going to calculate the sleep error. And then right here, we have the stuff that does the average of the last 60 frames. You notice it's an array. And then we have a frame index right here that goes over and tells us what frame to write into. And for debugging purposes, et cetera, you might want to keep the frame count because that will be very useful in future development. Okay? So, the start frame is fairly straightforward. All we do is we basically say, in the start frame, we just say frame start time equals get current time. So we're not going to show that code. So at the end of the frame, there's a couple of things what we have to do. One is, the first thing is we have to calculate how much time we spent updating our game. So if you recall, when we go back here, at this point, at the point that the end frame is called, it's right here.
right here, right there. And what we need to do is calculate how much time we want to do this, and we're going to sleep for some time, and then we're going to busy wait. So we need to do the calculations that allow us to do this. Okay? So we calculate the time left. So time left is the target frame time, which we calculated in our constructor, the frame elapsed, and then some sleep error. So assume it's 0 for now. Just assume this is 0 for now. So basically, the time left is the amount of time that we're supposed to be in this frame minus the amount of time that we've spent working, and then we're going to do that. Now notice we also have this idea of delta time here. We're going to calculate this at the end of the frame after we do all our waiting and busy waiting, etc. Now, there's two things that can happen at this point. Time left can be greater than 0. That means that we have a budget of time that we need to waste or wait before we start the new frame. If we are out of time, i.e. the time left is less than 0, that means that we're running behind, and so we really need to just kind of not even adjust for any error, so we set our sleep error to be 0. Okay, so if we are running out of time, if we're running behind because something in our game went a little bit too fast for that frame, we basically reset our sleep error. So we have time left is greater than 0, so we have to do some waiting. This here is, how many seconds are we going to wait? And so right here we're going to, this is the amount of time that we are going to say we're just going to busy wait. So what we do is we say, okay, we're going to call sleep with half the time left. We're just going to make a very kind of good guess at how much time we want to wait with the sleep. We're just going to divide that by 2, so we have lots of latitude at the end of it, and then we go into here. So if the sleep requested is greater than the sleep threshold, that means that we have decided that we're going to use the operating system sleep function. We are going to do the following. We're going to get the current time just before we call the sleep. Then we're going to call sleep right here, right? Remember that this sleep requested here, this right here, is half of the time left, which we calculated up here. Right here, calculated it right there, right? When this function here returns, we then calculate the value of how much time the sleep requested overshot. So we get the current time, we subtract that from the time that we started, that gives us the time elapsed, and then we say we subtract the time requested, and that's going to give us an error. We calculate the standard sleep error to be the maximum of 0 and sleep error plus overshoot. So if the sleep is coming in below time, if it's coming in early, which it mostly never does, we set our sleep error to be 0. And if we basically take our overshoot and we add it to our error, but we only add half of it because we don't want to completely overcompensate because it might have been just a mistake. So what we're going to do is going to make sure that our sleep error never gets below 0. But here what we're doing is we're adding the overshoot a half of it. And this will allow us to get close to the sleep error that our system is doing, right? So once we are done with calling the sleep function, we busy wait. We just use this format here. This is pretty much guaranteed to end exactly on time. So there we have it. We have our end time frame, We come in here, we calculate the time that has elapsed up until now, right? Then we are going to evaluate our time left here. Now our time left is the target frame time minus the frame elapsed and minus the sleep error. And we'll do a little analysis of this in a second. But as I said before, sleep error starts at 0, and then if we overshoot, so when we ask for a sleep time here, when we ask for a sleep, it's going to overshoot. That's what we know about operating systems. So we increase our sleep error by a little bit. So if we overshot by 10 milliseconds, we're going to add 5 milliseconds to our sleep error, so that when we go back here, we're actually asking for sleep that is 5 milliseconds less, right? That's how that works. Now we need to calculate the total frame. So we're just going to be absolutely sure that we are calculating the exact amount of time that has occurred up until this point. And so we do this thing here. There it is. Our total frame time is the current time minus the frame start time. This is an absolute truth. There's no other stuff. And then we are going to set our delta time, which is for simulations. That is going to be the total frame time. If for some reason we're running really late, we're just gonna, if this is a really, really large number because we paused our game engine or something, we'll just set it to 1. And then what we're going to do here is we're going to record this in our circular buffer. If you recall, this circular buffer has 60 elements. The frame index, which is this one here, starts at 0. So then we add our total frame time right there. And then we increment our frame index by adding 1 to it. And then we take the modulo of the frame times, which in this case is 60. So on the 60th frame, this becomes 0, and then it iterates. And so once we've run 60 frames, the average of our previous 60 frames is kind of the average time that we're spending on our frames is the average of this array, which we can calculate very, very fast. Some people initialize this to be all zeros, and others initialize this to just be the target frame. So you start off with a reasonable stuff like that. Okay. So why do we need this error correction? We don't really need to do this. We could just busy wait for the whole time, or we could just guess. But our sleep function here is a little bit inaccurate, as we know. So we want to make sure that we are using this the most efficient way. So let's dig into this. So when we overshoot, we calculate our actual sleep minus the sleep requested. So the sleep error, we add half of this value. And then this thing here is clamped to be 0. So this can never be negative. And so on the next frame, as I discussed before, our time left is the target minus the work minus the sleep error. And then what we're going to do is we're going to ask for half of that sleep. Now you notice that if we overshoot by a little bit here, then we're going to request a sleep time which is slightly less because this value here is positive. So that means that this is a little bit smaller. And so what we're doing here is we're asking for just a little bit. So how does this look in real time? Let's say that we have a frame 1 where we do some calculations and we have 11.67 milliseconds left. So we ask for half of that, but the actual sleep is 6.03, right? So we've overshot by 0.2 milliseconds. So my sleep error here is 0.1 milliseconds. So now I'm going to ask here, you'll notice that my sleep requested is slightly less, and the actual sleep is actually just overshoots by a little bit, so I'm overshot by 0.02, and so I add half of this to my sleep error, and now I have 0.2. Now in this one, when it repeats like that. So you see how this is gradually incrementing, so that this number here and this number here is actually getting closer, because we are using the sleep error here, right? These numbers here are kind of roughly the same, but these are compensating such that our sleep is actually doing the better thing. So if we're running behind, we're running over budget, we can't do anything. We just have to we just have to reset everything. So we set the sleep error to be 0. We also make sure that if the sleep comes back in early, we can we don't want to be under asking for sleep time. The scheduling noise is bursty, so we're going to be conservative. So we basically multiply both the time requested by half and the noise by half, just because these things are fairly kind of a little bit random here. So, and that's this is noisy because you might have one frame here that overshoots by 20 milliseconds because some other process grabbed the CPU. But if you add that 20 milliseconds to your sleep request, then you could undersleep badly, and that means you're going to spend more time busy waiting. So we are obsessing about these small numbers here because they actually do make a difference in terms of performance, CPU heat, and all of that stuff. And so the circular buffer, basically what it does is we start off, and if we're frame 58, we have filled up all of the data to here. And I said this could actually be the target frame rate, or we could set it to 0. If we set this to 0 here, then we can't really report an average frame rate until we have 60 frames. So that's only 1 second, so it doesn't take that long. And so now when we go here, we fill in this one here, the 59th frame. The index gets wrapped to 0, and so frame 60 data goes in here and overwrites the frame 0 data gets overwritten with the frame 60 here. And so you can see that 61 will be here, 62 will be here, and et cetera, right? And so get FPS averages all 60 entries and always the most recent 60 frames. Okay. We'll come back and we'll talk about input handling and how we are dealing with something that needs real-time interaction. I'll be back in a second. Okay, we're back. Let's talk about input handling. So we're kind of moving towards our little baby engine. We've talked about how to represent our data. We've talked about how objects in our data are basically rows in a spreadsheet, and that we have components on those rows. So each entity is like a row, and then we have data in it. Let's see how we deal with input, right? So SDL provides 2 ways of getting data. One is it will actually tell you when a key has been pressed, when a key has not been pressed. So these are called events. And so every time you call SDL poll event, every time SDL gets an event like a key press or a key release, it stores them in a loop. And then you can go and ask at the beginning of the game loop, say, hey, did we get a quit event, or did we get escape being pressed down? And in both of these cases, we're just going to set this variable running to be false, which indicates that the game is over. So for example, if you don't like escape being the key that exits the game, you could go and find this to be something else. You could use Control or Alt or any other thing. Yeah, you can play with that. The other thing is that SDL maintains a keyboard map of all of the keyboard keys that are being held. So a keyboard is either up or down. So each key has a constant that's defined. You can look that up. And so in this particular piece of code here, if this key, which is labeled SDL scan cone up, that's the up arrow, this will be true if up is being held down at this particular point in time. So again, there's two ways that we can get data from SDL. One is this one here. It tells us an event that something has happened. And here we have the keyboard state. Now, as many of you know, when you are typing on your computer, you get an event for a key down, and then you get key repeats, right? But there's a gap between the two. So if you want your game to have a action that happens when you press a key down and continues to happen, this is an unreliable way of doing that, because you're waiting for some system to generate events, and what you're going to see is, so for example, if I was going to use the up arrow, I would have here the SDL escape, it would be SDL scan cone up here. I would get a delay. We don't want that. So let's see how we can use this one in particular to get very, very quick responsive action, so our game feels nimble and fast. And then we're going to just use this one here so that when we finish the game, it just exits, right? So this one, all we care about here is, hey, did you press escape or did the end? Okay, in that case we're done. But this is the one that we're going to focus on, is how do we use this particular thing that we can call every frame to get nice fluid motion input from the player. So we have been talking about representing the data within our game as rows in a spreadsheet, entities that have components. So at this point we have added a position, a size, and a color to get our little rectangle. We're going to add a new component, which is the input component. You're like, wait, this is, what are you doing adding this as a component? We're going to add an input component to any entity that responds to input, right? So in that row for that entity, we're going to add the state of the up, down, left, and right arrows. So this is a component. Why are we using this as a component? Because I'd like to be able to write my system such that it just looks for entities that have input components and just processes those, right? So I'm not going to use it as a global variable. I'm going to use it as a data that's on the system, and then data that's on the entity as a component, and then the systems will process it. So what we are doing here is we have an entity here, and then we add the data, and as we will see, the systems process it down the line. In fact, what we're going to first show is that we're going to build a system that actually adds the data to the entities, right? So let's have a look at that and see how we do that. First thing we're going to do is we're going to deal with the brutal events, which is escape and quit. If you hit escape or you close your window, we set the game running to false and we're done. If we have not ended the game, what we want to do is we want to find all of the entities that are looking for input. So we've set up a bunch of rows in our spreadsheet, and then we ask, say, okay, give me all of the entities that have an input component, right? Um, then once we have that, I get the component. What I'm doing here is I'm just getting the component. I'm getting a pointer to the component. Now that component has an up, down, left, and right uh, variables, and so I simply copy the value of the current state of the up arrow into the up uh, variable of the component, and I do exactly the same thing for the down. That goes here, left goes here, and right goes here, right? So that's it. So notice that there's no logic here. Notice that there's no bookkeeping. I'm not keeping track of, oh, the key was pressed down 10 frames ago, and I haven't received an up event, and so it's just the state of the keyboard. So the absolute truth about what the keyboard is right now. There's no event. There's no OS repeat issues. And just try it in your keyboard. Hit go in and press a key, and notice that the keyboard, the value of the key enters, and then there's a little gap, and then it repeats, right? And you can set those up in your operating system. That's a horrible experience if you're playing a game, right? You want to be able to press up, and the character starts moving up immediately, and when you let go, it stops. So let's see what's happening here, right? So right here, let's go through the control flow. The user holds the up arrow. SDL detects that the arrow is up, and it was now setting the value of the keyboard up to be true. And so this happens at the operating system level, and SDL is running there. So it's actually running a layer, and it's going to scan the keyboard every frame, and it's going to set this to be true, right? And how SDL does this is none of our concern. All we know is that at the beginning of this frame, I set my input up to be true, because what I'm doing is I'm asking SDL for the value of this variable here, and I'm going to just add it to my input component, right? So I've done that in this frame. The next frame, my movement system, which we'll be talking about a bit later, it reads the input up here, which actually happens to be true, because we had, it's data on that entity. And so what we do is we basically go, oh, okay, we're going up in a 2D game, positive y is up, so we're just going to take the speed times the delta time, and we're going to make this position go up. And now a number of frames later, so a whole bunch of frames occur here. So this here keeps happening so long as this is true, right? So this can be 100 frames, this could be 1,000 frames, it could be 1 frame, it could be 2 frames. When the up arrow key is released, the SDL system sets this to be false. And so now that next frame, right after that happens, I set my input up to be false. This reads that data as false, so there's nothing to do. So right here, it's false, we don't do anything, and we continue with that, right? So now notice the flow here. The user presses the up arrow, SDL, the underlying system, just maps that to a keyboard thing. So I'm going to have two systems here, right? I have an input system, and it's looking every frame, it's looking at the value of this SDL value, and then it will set this particular component on our entity. That row that has a component gets this value set to true. Then the movement system runs, right? And it goes and says, okay, I found this entity that has an input component, and I look to see if it's true. Because it's true, I'm going to increase the value of the position y according to the speed times the delta time. So I get a nice smooth flow. And then this here is happening, this frame, and then it goes back. Nothing has changed. It goes back and keeps repeating. It goes around again. And as long as I'm doing this, my frame is advancing. Now notice that the movement system is very simple. What it does is it looks for the value. If the input is up, it updates the position, the y position of the object, and it doesn't do anything like rendering it different or anything. So the movement system itself is actually very, very simple, and that's the whole point of what we're trying to do here. Okay. Next, we'll talk about the blackboard, the global state in ACS, what we're doing, and I'll be back in a second. Okay, we're back. We've talked about what we talked about in this particular section. Let's quickly go and review this. We have talked about the timer, right? We talked about the timer. We talked about maintaining 60 frames per second so we can get that nice, beautiful, smooth motion there. We went through the details of the timer and how to go through and make sure that we're handling that. The next thing that we did was we talked about events and input and how we can use the keyboard map from STL to get our data. We talked about the flow, and we showed how this particular setup allows the movement system to just keep doing the right thing as long as that component is set to up. Now, we've talked about entities, components, and systems. What we're going to talk about right now is something that we've told you you should never do. We're going to have global variables. So we need some sort of global state for these environments. For example, delta time. Delta time is the amount of time that we spent last frame. And that means that we're updating our simulation, our movement speed, all goes according to that. Where do we store it? We could store delta time on every single entity. This is a lot of entities that are going to be using that. So where do we store it? It might be a waste of kind of memory and time to store it there. Window dimensions. Window dimensions are global property. The rendering system needs it. Maybe the movement system needs it, but it's metadata. The frame count. We don't really need to add the frame count. We showed that the timer system is going to store the frame count, but we're not going to put that on every entity. Some systems may use it, but we don't necessarily want to have that on every entity. These are global properties of the world, not of individual entities. So let's go through and think about this in a kind of more detailed way. Think of this like a stage play. The entities are the actors that are on stage. The components are what the actors are wearing. So, if you look at an entity, it's a human being, and that human being is wearing a Roman gladiator outfit, and that way you know that this entity is a Roman gladiator. And then the systems are the directors that tell, hey, gladiators, all of you move forward. And then the blackboard is the stage itself, the context in which everything happens. So the stage does have some properties. It has lighting, temperature, dimensions. So our game has a window size. Our game has a color scheme. All of these things. The analogy does start to break down, but that's how you can think of it. So We could actually create an entity that just stores everything. Um, we could have a world entity, but it's not a game entity. It's the world, and it actually pollutes all of our entity queries. And the access pattern is kind of odd because you would have to go and if you're trying to render an object, uh, you also then have to go look at another entity, which is a world, to get the size from there. And basically, you're going to get this kind of God component, God entity. The other one that you don't want to do is have this set of global variables, because we can't unit test them. There's all sorts of hidden dependencies, and we have a namespace pollution. And so again, it's thread unsafe. That's not going to be an issue in this course, since everything we're running is single-threaded, but we will actually, in the future, that would be good. So these are the two kind of things that pop into your mind and say, oh, since we have entities, let's just make a world entity, and then I'm going to add a component delta time, I'm going to add a component window dimensions, I'm going to add a component operating system, I'm going to add a component network connector, all of these kind of global data we add it there. Then we have this component, a single component that potentially every system is looking for. And this one here, you can't test this. You just basically magic numbers that are in the global variable. So what we're going to do is we're going to create a blackboard. It's a centralized key value store, right? So what we are going to do is we are going to have a blackboard that is going to have a map of values, and we going to give it a set. We're going to set a value, and then get is, this is my get value. So this is the type, so I can store objects of any type, and I basically when I ask for a value for the string, I go find it in my data. If I did not find it, I can throw this entity and say I did not find it. Otherwise, I return that item. You shouldn't be writing code that looks for data in the blackboard that isn't there. This should be treated as a serious error in your game. Why are you trying to access data from the blackboard that isn't there? So leave that in there, so that if you ever make a mistake and you try to read data from your blackboard that doesn't exist, it will throw an error, and then you can go and debug it. This is kind of a perfect example of how to use exceptions in writing code. So we take this pointer that we found here, we cast it to the type that this is expecting, and then we can also add this value here. So the pattern should be that you say, if the blackboard has this key, then get this key here, right? So the timer, let's have a look at it. So the timer update blackboard is going to set a double value for delta time. It's going to set a double value for FPS, and it's also going to set the frame counter. Notice that we're setting a double for the delta time, a double for the FPS, and an int for the frame count, right? This blackboard is an explicit dependency. We pass it in as a parameter. There's no hidden data, and there's no kind of anti-patterns here. So when we want to read the data, so my movement system, there's the movement system that we're going to talk about right there. Remember back here, let's see, we were back here, we talked about the movement system right here, right? So let's go have a look at the movement system. Isn't this exciting? We actually have a system that's going to make things happen. So the first thing we do is we get our delta time from the blackboard, right? So here we are. We have our movement system takes in pointer to the component storage, and we're going to add this as an explicit dependency, which is our blackboard. So the movement system has access to all of the entities and the blackboard. So we get the delta time here. We need that because of our movement. And now I'm going to go here and I'm going to query my component storage for all of the entities with component position. So I'm going to get all of the entities in this game that have position, and then I'm going to do a query and say, okay, do you have position? I know you do, so that's fine. You may have position and you may not have velocity, right? That's also cool. So if you have position, if you don't have position or you don't have velocity, then you're going to continue. At this point, this is always going to be true. This may be false. Now we get the value of the position and we get a value of the velocity, right? Now here's where we actually start to make a game. I have the component for this entity, which is a position. I also have the velocity, which I got from the component, and I have delta time here, and so I can use this to update the position x, because if you notice, this is plus equals. And then I do exactly the same thing for my y position, right? Now, notice that this movement system didn't care about keyboard. Now, something else set this value here, right? If this value here, let's say that if we press the up button, so this would be 0 and this would be 1, then this would move the object in the up direction. If I had pushed the down button, then this would be -1, so then this would decrease. If I had pushed the left button, this would be -1, this would be 0, so then this moves the object in this direction. If I had pressed the right button, then I'm going to push the object in that direction, right? That's the magic of ECS, is that this particular movement system is now able to move my object in any direction that is set by whatever system sets the velocity for this object. But the key component here is that we do this as a single call into our blackboard, and then we process all of our entities in here, all of the entities that need movement, and we just get their velocity. We multiply the velocity by delta t. We typically think of velocity, we're going to think in this course of velocity as speed per second. So delta t is the small delta of time, and so this will increment it such that over 1 second we would actually travel this distance. Now, we spent a lot of time talking about components, and now we've introduced this idea of a blackboard. When do we use which? So you're thinking of how to, you're building a new feature for your game, and you think, I want to add this particular piece of data. I want to have the data, so does this data belong to a specific entity? is there one particular entity in the game that uses this. You can have multiple entities. Let's go here. Sorry about that. Position, velocity, size, color, health, input, AI. Global variable, anything that isn't tied to an entity, is going to be the blackboard. So we're going to use delta time, frame per second, frame count, window width, game state, pause running. And in the future, one of the futures, we're going to be able to pause the game and single step through it. This is all data that we will see that belongs in the blackboard. And here we're going to use components. Now you might say, well, input, that sounds like a global entity. Well, some entities may want to have the keyboards up and down, and others may, for example, you may have keys that are attached to movement, and then you also have keys that are attached to things that it happens, like jump or fire, that are processed by different systems. So you could have different input parameters on different objects, and that's perfectly okay. So the unit testing with the blackboard is actually very straightforward because we're building a key value component. This is what our test case looks like. We basically set up our storage, set up our entity manager, then we do our tests, etc. Right? Okay, now let's take a break. We'll come back and we'll talk about our first real system. We're actually going to get something to move in response to a human interaction in our game. Okay, let's get moving. Literally, actually, let's get moving. We are going to add a new component, velocity, here. We already have position. What we're going to do is now add velocity. So when we have a object or an entity that has a position and it also has velocity, we're going to say that that is the signature, or those are the components that are required for this entity to move around. So let's see how we accomplish that. Here is our first system, the movement system. We previewed it before, but we're going to dig through it again. First thing we do is we go to the blackboard and we get our delta time. So delta time is the amount of time that the last frame took, right? Then here, we're going to go and ask for all of the entities that have a position. Now that I have an entity that has a position, I know that this is going to work, but I don't know whether it has a velocity component. If I don't have a velocity component, then I ignore this entity. I just move on. If I do have a velocity and a position, I'm going to get the pointers for those two components. Then I'm going to update my position by whatever velocity this is, as we talked about before, times the delta time. We don't care about input. We don't care about what entities are. All we care about is that you have a position and you have a velocity. You could be a player. You could be a player entity. You could be an enemy entity. You could be a background character entity. If you have a position and you have a velocity, this system will take care of it. So this system doesn't care about what any entities. It basically does a query with the right components. So if you have the right components, i.e. position and velocity, this system will operate on that. Don't do this. We have defined our velocity as pixels per frame, per second, not per frame. If you do this, velocity will move that many pixels per frame. It'll go ridiculously fast. what you want to do is this one. You want to compute the delta. So the reason that we do this here is that this is the amount of time that elapsed last frame. So we use the delta time from the last computed frame to be the amount of time. So we're going to multiply the speed of pixels per second times the amount of seconds that occurred last frame. Now, if I multiply this by 60, this cancels out and becomes 1. Now, if, for example, if for some reason I'm now running at 30 frames per second, my delta changes. So again, I have 100 pixels per second here. Right? So the goal here is that regardless of what FPS you're running at, the perceived speed is the same. If you remember from that animation that we saw at the beginning of this video, the speed of all of those squares that we're running across was the same in terms of pixels per second. So same speed, any frame rate. This is what allows it. And if you do have a situation where your frame rate is for some reason a little bit out of control, this here, because we are getting this from the blackboard and the blackboard is being updated by the timer, then if the last frame actually was, for some reason, took a long time, then we're going to have a slightly bigger delta time, and that means that the amount of pixels per second is consistent. So now let's connect our input to movement. So there we go. This is the part that we have all been waiting for. I'm going to add a player control system, right? So this is a system that I'm going to add, and I'm going to have in this game, this game that we're building right now, we're just going to have a player run around, right? And so I'm going to look for all of the entities that have an input component and have a velocity component. And if I have the input component and I have the velocity component, if I don't have them, I skip. I get both components here. Now, in the previous example, I talked about if you have the movement system reads the velocity dx and dy, and then does the movement update. So what are we going to do here? Our very, very simple game here is going to do the same thing here. At some point previously, the input has been set on this entity, right? If no keys are pressed, then none of these are true, so this particular speed is set left at 0, right? So notice that every frame, we take the velocity, we reset it to 0, and then we check the input. Remember that the input here came from the SDL subsystem that mapped the keyboard state to the input on this particular entity. And so what we're doing here is we're taking the velocity, which we got here, 200, right? So we've hard-coded the speed for this example. In general, this would be, you could have another system that sets the speed and you could read that, etc., etc. So, but for now, we are trying to move at 200 pixels per second, and we are going to use the arrow keys to go up and down. So the systems run in a particular order. In this particular case, we have our input system here that basically maps the STL events into input components. The player control system, which takes input and maps it into velocity. Then we have the movement system that maps velocity in plus delta time into position, and then we have the render time, right? This is how we are transforming our data. The keyboard, which is an operating system, goes into STL events or keyboard map, and then we have a system that maps that keyboard map into the input component, and then we have a system that looks at the input components, sets a velocity component, and that velocity component, if it's present, updates the position component, and then that gets rendered to the screen. So each one of these is a data transformation. Each one of these is a system that is actually processing the entities and either updating components or adding data to components. Okay, so we'll come back to the final part of this lecture of putting it all together. Okay, let's see how this all works together, okay? We talked about a timer that allowed us to maintain 60 frames per second. We talked about input. This is a new concept. We basically take keyboard events and we use STL to update input components. We had a global data store, our blackboard. This is going to allow us to store data that's available to the entire game. And then we talked about a system that's going to allow movement. So let's have a look and see what this is going to look like. We are going to introduce you to a game where we can run around and we can make things happen like this, right? The way that this happens is that we have an input system here that maps the STL keyboard map into input data. Then we have a player control system here that takes any component that has an input, any entity that has an input component, and it updates the velocity. And then the movement system takes the delta time from the blackboard and the updated to the velocity from here, and it moves the object, and then the render system. So basically what happens is that the movement system looks at it. We have the square here. If there is an upward velocity, it will render here next time, and it will render here next time like this, right? As we go, we can have a look at this and see. So here I'm going to press the up arrow, and then I'm going to stop. And what you're going to see there is that right now the movement system is running, and it's updating the position of this by adding 0 to it every time. So because there's no input here, this thing leaves the velocity at 0, and this thing makes a movement. So notice that the movement system doesn't have to detect whether any keys are pressed or not. This thing here informs this system here that the keys are pressed by updating a component on an entity. We don't care here whether a key was pressed or not. All we care about is that the velocity and the position get added, and this render system, it doesn't care about the velocity, it doesn't care about input systems, it just cares about where the position and the color of it is. So what does this look like? Let's go through the code and just have a quick look here. We have our STL window. We create our STL window. Let's go here. We create our STL window. Here we create 3 managers, an entity manager, a component storage, and a blackboard. These are our kind of 3 global objects. We set the blackboard to be the width. Notice we only set the width and the height here. We don't go and set the delta time here, and we don't set the FPS because that's going to be published by the timer after every update. And then I add my very first player. It is a player that has position, My position is 300, 400, 300. It has a velocity. It's 0. That is a placeholder for our player input system to change that when we're moving around. It has a size, a color, and it also has an input, right? So these are the 5, 1, 2, 3, 4, 5 components that we have. We set up our timer with a required frames per second of 60, and then we use that timer to update the blackboard. This is going to write into the blackboard what the current delta time is. Then I'm going to implement a render system, I'm going to input an input system, I'm going to input a player control system and a movement system, right? These are the systems that are going to be running, and I set my Boolean running to be true. Then I process my input systems. I use the player control system to update the data. This will look for any entity that has an input system and a velocity system and a component, and it will add it. Then I take my movement system, then I display everything, and then I'm done. And at the end of the day, I update my timer update so that the next time around my delta is correct. What you'll see, well, this is kind of the representation of it, but this is what you're seeing, right? We're seeing this little red square going around as like that. So what is happening here? Let's have a quick look at this. The user presses the up arrow here, right? SDL makes that available as a key map. The input system then says, oh, hey, wait a minute. I need to set the input up to be true because you have an input component. So the input component here gets input to be true. The player control system executes next, and it reads from input, and it sets the velocity to be 200. The velocity component now has a value 200. My movement system reads it, and it takes the 200. It gets the delta time from the blackboard, and it updates the position of X, which is right here. And now our position has increased by 3.3, and so my render system now displays that in the correct way. And then we go around and around and around and around as long as this is happening, right? The way that we've implemented our movement is that we can achieve 200 pixels per second at 60 frames per second or 30 frames per second. I'd encourage you, when you start playing with this, that you change your frequency in the timer setup, and you'll see that, change it down to 5 frames per second. You'll get a very stilty kind of jumpy game, but you'll actually see how that works. So the system composition is the power. This is the power of what we're doing, right? We have the same components, different combinations, and different behaviors. So the player controlled entity has position, velocity, size, color, and input. And the systems are, we have an input system, we have a player control system, we have a movement system, and we have a render system. Our AI controlled system in the future, in fact, you'll actually have kind of the bounce system, but basically the difference between a player control system and an AI control system would be this thing right here. In the assignment, in this particular assignment, this is going to be your bounce system. And static entities have position, size, and color. No inheritance, just data and logic working together. So let's pause there, and then we'll come back to the workshop overview. Thank you very much. Okay, so what we are going to do now is we're just going to talk about the workshop overview and the summary of this class. What we want you to do is build a bounce system and multiple bouncers. In the exercises, we walk you through step by step of how to create a new bounce system,
that reverses the velocity for non-player entities hitting a wall. So what does this look like? Well, here's my implementation of that. Um, Here we go. As you can see, I have my player entity in here that's being controlled by me. I could pretend that I'm trying to avoid these things, but there's no collision, so you could actually kind of pretend that it's a game. I don't know. But as you can see, this 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 guy here, the yellow guy, when they bounce there, he bounces there. So if I kind of follow them here, he goes up here, he bounces there, goes there, and goes there. So, and because each one of these have different speeds, see if I can keep up with the blue one. It goes up there, the blue one goes up to there, there, there. So you can see the blue trajectory going like that. So this is what you're going to be doing. All four of these objects that I've added here are being controlled by my bounce system, right? And so let's have a look and see. These non-player entities are going to be players that don't have an input, and so you're going to build a system that looks for any entity that has velocity and position and doesn't have input, and that's how we're going to do it. And so what I want you to do is experiment with this, change the speed, change the size, transparency, break it if you can, test it with 50 entities or something like that, and then you're going to describe what you tried in your LLM assessment, right? And so I want you to create a bounce test.cpp, test output.txt, multiple bouncing.png, and an LLM assessment.md. So, and that's all detailed in the exercise document that you see on the website. The what we covered today was we did the timer, sleep, and busy wait so that we can get precise framing and we can get nice smooth movement. We talked about how we're going to get input into this new component, this ECS. So we added this input component and we showed how that can be used by the player update. We introduced the idea of a global state management for timing of world data. Then we introduced our new movement, which is frame rate independent position that uses delta time. Please compile your game at 5 frames per second, and you'll see that it actually moves around. The pattern that we have is every system reads data from components and or the blackboard, processes the data, and it writes the results back to the components. So this makes things very simple. What we are going to be doing next class is we'll introduce a heads-up display and resource management so we can bring fonts and images into our game. Thank you very much. See you all later. Bye.